Before a neutron star is born, matter still belongs to the familiar universe of atoms, heat, pressure, and light. A quiet star burns for millions or billions of years, holding itself in balance while gravity presses inward and fire presses back. Inside that balance, hydrogen becomes helium, photons wander slowly through glowing plasma, and tiny neutrinos slip away from the core like faint messengers crossing the dark. Nothing seems hurried, nothing seems fragile, yet every star carries a hidden threshold within it, a place where ordinary matter can no longer remain ordinary. When the fuel fades, when the pressure changes, when gravity gathers too much strength, the calm structure of a star begins to search for a new way to survive. In that search, white dwarfs appear, quantum rules rise like invisible supports, and deeper still, in the ashes of massive stars, neutron stars come into being. This journey is built for rest, for slow listening, and for drifting gently through the most extreme matter in the universe without needing to hold every detail. We will move from the surface of the sun to the cold crust of a neutron star, from plasma to degenerate matter, from nuclear pasta to strange possibilities hidden in a core no telescope can directly see. The pace will stay unhurried, the images will be clear, and somewhere in the silence between gravity and pressure, the universe will feel both vast and strangely still. The sun appears, from far away, as a smooth and steady circle of light. Its edge is clean to the eye, its color softened by distance, its presence so constant that life on Earth has learned to treat it almost as background. Morning follows night. Shadows shorten and lengthen, leaves open, oceans warm. The star at the center of the solar system gives the impression of a lamp that has always been burning and will keep burning without effort. Closer in, that quiet surface loses its simplicity. The sun is not solid. It has no ground, no hard shell, no calm skin that could be touched and held. It is a vast body of hot gas and plasma, layered by pressure, stirred by heat, and bound together by its own gravity. Across the visible surface, pale granules rise and fade like slow bubbles in a boiling sea. Each one is a cell of convective motion, a place where hotter material comes upward from below, releases some of its energy into space, cools slightly, and sinks again. The pattern looks fragile. It is not fragile at all. This visible layer is called the photosphere, the region from which most sunlight finally escapes. Above it, the chromosphere lifts in a thinner wash of red and pink light, normally hidden by the glare below. Higher still, the corona stretches outward in long, faint streamers, so thin that it seems almost empty, and yet so hot that atoms there lose many of their electrons. During an eclipse, when the moon covers the bright face of the sun, the corona appears like silver breath around a black disk. It is one of the few moments when the outer atmosphere of the star can be seen with ordinary eyes. Under the photosphere, the motion does not stop. The convective zone carries heat outward in broad rolling currents, each one shaped by the slow struggle between rising warmth and downward weight. Magnetic fields rise through this moving material. Darker patches gather where the field slows, the upward movement of heat, and bright arcs of plasma sometimes follow invisible lines far above the visible light. Beneath that, in the radiative zone, energy moves differently. Photons do not fly straight to the surface. They are absorbed, scattered, re-emitted, and turned aside again and again by the crowded material around them. A particle of light, born deep in the sun, may take a very long time to reach open space. The journey is not a line, it is a drift. All of this motion hides a quieter fact. The sun keeps its shape because two tendencies are meeting one another at every depth. Gravity pulls everything inward, trying to gather the star into a smaller and denser form. Heat and radiation press outward, not as a single wall, but as a constant response from the material inside. The star is held between them. It neither flies apart nor falls inward. It stays wide, round, and luminous because each layer carries the weight of the layers above while also being supported by the layers below. This balance is called hydrostatic equilibrium. The phrase sounds formal, but the image behind it is simple. At every point inside a star, pressure is pushing one way and gravity is pulling the other. If the pressure weakens, the star contracts. If the pressure grows too strong, the outer layers expand. Stability is not stillness. Stability is adjustment, repeated across the whole body of the star, from the thin outer atmosphere to the hidden center where the pressure is far beyond anything found on Earth. The material itself changes with depth. Near the surface, some atoms can still hold on to some of their electrons. Farther down, heat and pressure strip matter into a more open state, where nuclei and electrons move separately through the star. This is plasma, the common substance of stars, though it is uncommon in human life. It glows, conducts electricity, follows magnetic fields, and carries energy in ways that cold solids and quiet liquids do not. A flame gives only a small hint of it. A lightning bolt comes closer, though it lasts for only a moment. Inside the sun, plasma is not a bright mist floating freely. It is dense, heavy, and deeply compressed. Every layer bears the weight of a great amount of star above it. The deeper the descent, the more closely the particles are forced together. Hydrogen nuclei move fast in the heat, repelling one another because they carry the same positive charge, yet pressure keeps them crowded. In the core, the conditions become strong enough for a few of them to overcome that repulsion. They meet, they fuse. Helium is made. Fusion is the source of the sun's long patience. A small amount of mass changes into energy, and that energy spreads outward through the star. It does not escape quickly. It is held, redirected, softened by distance and time. By the time sunlight reaches Earth, it has become gentle enough to warm skin, grow forests, move winds, and paint the surface of water with gold. Its origin is far less gentle, in a core where matter is pressed so tightly that ordinary ideas of gas begin to fail. The sun is therefore not a simple fire. Fire consumes material by chemistry, using electrons and bonds between atoms. The sun shines by nuclear change, by the rearrangement of the centers of atoms themselves. It is a slow furnace only from the point of view of the surface. Deep inside, the energy is born in rare events among countless particles, and the star's great size turns those rare events into steady light. There is a restraint in that steadiness. The sun does not burn through its fuel all at once because gravity, pressure, temperature, and density settle into a measured relation. If the core cools slightly, gravity compresses it, fusion becomes more active, and heat rises again. If the core warms too much, the added pressure allows it to expand, and the fusion rate eases. The star corrects itself without intention. It has no mind, no choice, only physics repeated through layers of plasma. This self-correction is the first form of safety in the long story of dense stars. The sun is not close to becoming a neutron star, and it never will. Its mass is too modest for that final path. Yet it provides the gentlest doorway into the same deeper subject. Matter under pressure always looks for a way to answer gravity. In the sun, the answer is heat from fusion. In smaller stellar remnants, the answer will come from quantum rules. In the crushed remains of massive stars, the answer will become stranger still. For now, the sun continues its balanced work. The photosphere ripples, magnetic fields twist. Neutrinos leave the core almost without touching anything, slipping through the star, through planets, through empty space. Light follows more slowly, wandering outward until it reaches the surface and begins its open crossing between worlds. The star seems steady because its changes are hidden inside long timescales and great depths. At the center of this familiar light, the first lesson is already present. A star is not held together by strength alone, and it is not protected from collapse by brightness alone. It remains itself because matter, energy, and gravity have found a temporary agreement. The agreement can last for billions of years. It can fill a sky with morning. It is temporary, all the same. Far from the solar surface, On a warm plain in eastern Bengal, another kind of pressure gathers around a young student. The year is 1905. The air in Dhaka hangs heavy over schoolrooms, river roads, and crowded streets where arguments about empire and partition move from whispered conversation into public protest. Meghnad Saha is still a teenager, not yet the physicist whose name will one day be tied to the state of matter inside stars. His family has little money. His education has already required scholarships and discipline. The partition of Bengal changes the texture of his world. British officials draw administrative lines across a living region, and those lines are felt in schools, markets, homes, and religious communities. Saha joins the protest movement, and the punishment comes quickly. He loses his place at Dhaka Collegiate School. For a young person whose future depends on education, the expulsion could have closed the path entirely. It does not. The interruption becomes only one layer in a much longer life, shaped by mathematics, astronomy, public service, and a belief that science belongs not only to laboratories, but to nations trying to stand upright. Years later, after study in Calcutta and a growing reputation for physical insight, Saha turns toward a problem that appears, at first, almost impossible. Starlight arrives at Earth thin and distant. It has crossed emptiness for years, decades, or centuries. It carries no sample jar from the surface of a star, no fragment that can be weighed in the hand, no grain that can be placed under a microscope. Yet hidden inside that light are dark and bright lines, marks left by atoms absorbing and emitting particular colors. The lines are like fingerprints, but fingerprints that change with heat, pressure, and the condition of the atoms themselves. The difficulty lies in the condition of those atoms. An element does not always show the same face in a stellar atmosphere. Calcium in a cool layer, calcium in a hotter layer, and calcium whose electrons have been partly removed can leave different marks in a spectrum. Without knowing how heat and pressure alter the atoms, a star's light can be misleading. An element may seem absent when it is only ionized into another form. A layer may seem chemically different when it is really only hotter, thinner, or more exposed to radiation. Saha's ionization equation gives astronomers a way through that confusion. It links temperature and pressure to the fraction of atoms that have lost electrons. It tells how much of a gas remains neutral and how much has crossed into an ionized state. In plain language, it describes the moment when atoms begin to let go. An atom is held together by electrical attraction. At its center sits a small, heavy nucleus carrying positive charge. Around it, electrons occupy allowed states, each one light, negative, and bound by the pull of the nucleus. In a cool and quiet setting, many atoms keep their electrons close. They remain neutral, their positive and negative charges balancing one another. Heat changes the arrangement, collisions become harder. Light brings more energy. Some are shaken loose and move away into the surrounding material. This is ionization. It is not the breaking of the nucleus. It is not fusion. It is a more delicate change, the loss of electrons from atoms that still keep their central identity. Yet the effect on matter is large. Once enough electrons roam freely, the gas can conduct electricity, respond strongly to magnetic fields, and carry waves and currents unlike those in neutral air. The material has become plasma, or at least part plasma, a mixture of charged particles and remaining atoms moving together in heat. The solar photosphere, seen from Earth as the bright surface of the sun, sits near this boundary. Its temperature is high by earthly standards, but not high enough to tear electrons away from every atom. Much of the material there remains only partly ionized. Hydrogen, the sun's main ingredient, holds on more strongly than many might expect at this layer. Metals, in the astronomical sense of elements heavier than helium, give up electrons more readily and leave their own marks in the spectrum. The result is not a single simple state. It is a changing mixture, a place where gas and plasma overlap. Above the photosphere, the chromosphere thins and glows, and ionization becomes more complete in places. Farther out, The corona spreads into space with such low density that its heat is not felt in the ordinary way. Its particles are few, but many are highly ionized, stripped by motion, magnetic stress, and radiation. Below the photosphere, density increases. The material grows more crowded. The deeper layers of the sun press atoms and electrons into conditions where plasma becomes the natural language of matter. A star, then, is not made of one substance, in one condition. It is layered not only by depth, but by the changing freedom of its particles. Near the outer visible light, some electrons still remain tied to atoms. Deeper down, they move in a wider sea. In the core, where fusion occurs, the word atom begins to lose its familiar meaning because nuclei and electrons no longer form the quiet structures found in cooler matter. Pressure, heat, and radiation have taken the material far from the world of stone, water, and air. Saha's work matters because it makes that transition readable. A telescope gathers light. A spectrograph spreads it into color. The equation then helps connect those colors to the physical state of the star. It becomes possible to say not only which elements are present, but how they are behaving under the local conditions. The star remains unreachable, yet its atmosphere becomes less silent. The same idea, in a softer form, prepares the way for denser places. Neutron stars are not plasma spheres like the Sun, and their interiors reach states Saha's equation was never meant to describe. Still, the path begins with the same lesson. Matter changes its character when pressure and temperature change. A familiar element can look unfamiliar. A neutral atom can become an ion. A gas can become plasma. Later, under greater weight, electrons will be forced into stranger arrangements. Later still, protons and electrons may be pressed together until neutrons dominate the story. Each threshold is different, but the movement from one state to another has already begun in sunlight. On the solar surface, the signs are gentle from a distance. Dark absorption lines cross the spectrum. Bright granules rise and fade. Arcs of charged material follow magnetic fields into the corona. None of these details announces itself as a doorway into extreme physics, yet the doorway is there. The same universe that permits atoms to hold their electrons also permits those electrons to drift away. The same rules that shape a faint line in starlight will, under heavier skies and deeper gravity, help explain the remains of dead stars. Saha's equation does not make the sun less mysterious. It makes the mystery more precise. The light that falls across Earth is no longer only warmth and brightness. It is also a record of atoms under strain, of electrons held or released, of matter crossing a quiet boundary. Before the collapse of massive stars, before the hard crust of a neutron star, before the dense inner layers where ordinary images begin to fail, there is this first loosening. An electron leaves an atom. A plasma begins. Deeper inside the sun, the bright surface is left behind, and the idea of light begins to change. Near the photosphere, sunlight seems ready to leave, already loosened from the star and able to cross space in clean rays. Far below, in the crowded interior, light has no such freedom. It is born, swallowed, scattered, and born again. Its path bends without memory. A photon that begins in the core does not travel outward like an arrow, but wanders through dense plasma in a slow and broken motion. The descent passes first through the convective outer layers, where hot material rises in broad cells and cooler material sinks back into the depth. There is motion here, heavy and rolling, hidden beneath the fine grain of the visible surface. Below that restless region lies the radiative zone. The name suggests light, but it is not a place of open brightness. It is a place where energy moves through repeated contact. Photons travel a tiny distance before meeting charged particles, then vanish into them, then emerge again with a new direction. This long delay gives the sun part of its calm. Energy made in the center does not surge outward at once. It is stored in motion, pressure, heat, and radiation, spread through the star so slowly that the surface receives a softened version of the core's work. The sunlight crossing a window on Earth has taken its final open journey in only minutes. But before that clean flight, its older history has been a deep inward wandering through plasma under weight. At the center, the sun is no longer a place where ordinary atoms keep their form. Hydrogen nuclei, mostly single protons, move in a dense sea of electrons and other nuclei. The heat is high enough for particles to move with great speed, yet speed alone is not enough. Protons repel one another because they carry the same positive charge. They need to come extremely close before the strong nuclear force can bind them into something new. Most of the time they do not manage it. They pass, glance away, and continue in the crowded dark. A small fraction succeeds. Quantum physics allows some protons to cross the barrier that ordinary motion cannot overcome. Step by step, through a chain of reactions, hydrogen becomes helium. The process is quiet, only because the star is so large. Taken together across the core, these countless rare meetings release the energy that keeps the sun from shrinking under its own weight. The balance is exact enough to last for a very long time, but not exact in the sense of stillness. The core responds constantly. If gravity compresses it a little more, temperature rises and fusion becomes more active. More heat increases pressure, and the pressure pushes back. If the core expands a little, it cools slightly. Fusion eases, and gravity gains room to draw the material inward again. The star breathes through equations rather than lungs. It adjusts without awareness, following relations written into matter itself. Those relations are gathered under the idea called an equation of state. It describes how material answers when temperature, pressure, and density change. In a familiar gas on Earth, such relations can be measured in a laboratory. In the sun, they must be inferred from light, from surface motion, from the behavior of sound waves moving through the star, and from particles that almost never stop. It is part of the reason the star has a size, a temperature, and a lifetime. The sun gives astronomers a rare advantage because it is close. Its surface can be watched in detail. Its vibrations can be measured. Waves travel through the solar interior, bending and reflecting according to the density and pressure of the layers they cross. From the outside, these motions appear as small rhythmic changes on the surface, too slight for ordinary sight, but clear to instruments that can read the tremor of the star. This practice, helioseismology, lets the hidden sun speak in slow pulses. Another messenger comes from the core itself. Neutrinos are made during fusion, and they leave almost immediately. Unlike photons, they do not spend ages drifting from collision to collision. They pass through the sun with little resistance, through space, through planets, and through the quiet matter of living bodies without being noticed. Their ghostly passage carries news from the place where fusion is happening now, rather than from energy that began its outward wander long ago. Because the number and type of solar neutrinos depend strongly on conditions in the core, they act as a delicate measure of that interior. A small change in temperature changes the rate of nuclear reactions. A change in reaction rate changes the stream of neutrinos. Detectors buried deep underground or under mountains wait for rare moments when one of these nearly untouched particles finally interacts with ordinary matter. Most pass through. A few leave a trace. From those traces, the heart of the sun becomes measurable. There is a softness in this kind of knowledge. No probe enters the solar core. No hand gathers a sample from the place where hydrogen is being remade. The information comes indirectly, in vibrations, in spectral lines, in neutrinos, in the steady shape of the star itself. Each clue is incomplete alone. Together they show a core that is hot, dense, and balanced. A region where matter is pressed hard enough for nuclear change but not hard enough to become a stellar remnant. The sun will not stay this way forever. The hydrogen in its center is being used, slowly and steadily. Helium collects where hydrogen once dominated. Over immense time, the balance will shift. The core will change its structure, the outer layers will respond, and the star will leave its present long middle age. Yet the Sun is not massive enough to continue toward a neutron star. Its future leads instead to expansion, shedding, and a white dwarf, a small, hot remnant held up by a different kind of pressure. That difference matters. In the living Sun, heat from fusion is the main answer to gravity. In a white dwarf, fusion has ended, and heat alone cannot provide the support. In a neutron star, even atoms have been crushed beyond recognition, and the answer must come from deeper rules again. The solar core is therefore not the destination, but the first clear lesson. It shows that stars survive because matter has ways of resisting compression, and each way belongs to a particular state of matter. In the core, pressure and temperature are partners. In the later remnants of dead stars, density will begin to take command. Electrons will be crowded until quantum rules become a wall. Nuclei will be forced so close that the border between one and another begins to blur. Still, the path toward those extremes is easier to follow after the Sun has been understood. Its balance is familiar enough to be pictured, yet strong enough to reveal the theme that will continue into stranger places. Light is still leaving the solar surface. Neutrinos are still crossing the dark without pause. Beneath the golden face seen from Earth, the core keeps its slow work, making helium, releasing energy, answering gravity with pressure. The agreement holds. For now, the star remains round and bright, suspended between collapse and release by the patient physics of its own interior. Long before matter becomes exotic, it must first learn how to endure weight. When a star like the Sun reaches the end of its long central burning, its light does not vanish at once. The change comes through swelling, cooling, shedding, and contraction, through stages so slow that a human lifetime would see almost nothing of them. The core, once supported by fusion, becomes filled with helium ash, and later heavier products of burning. Around it, the outer layers loosen. They drift away into space, thin and colored by radiation, leaving behind the exposed remnant that gravity has been shaping in the center. That remnant is a white dwarf. It is not white in the simple sense of paint or snow, and it is not a dwarf in the sense of weakness. It is a stellar core, uncovered, small enough to be compared with Earth, yet carrying a mass that may be close to that of the Sunday. Its surface is hot. Its light is pale. It no longer produces energy through steady fusion in the way a living star does. It shines because it still holds heat from its earlier life, stored in compressed matter and slowly leaking into space. In the winter sky, Sirius offers one of the gentlest entrances into this strange class of star. The bright point known as the dog star shines with a blue-white steadiness broken by Earth's atmosphere, which makes it flicker in shifting colors close to the horizon. Near it, too faint for unaided sight, moves Sirius B, the small companion once called the Pup. The pair orbit a shared center of mass over roughly half a century, the brilliant star and the hidden remnant bound together in a quiet gravitational dance. For a long time, Sirius B seemed almost impossible to understand. Its light suggested heat, its orbit revealed mass, yet its faintness implied a very small size. A star's worth of material appeared to be packed into a volume similar to a planet. The familiar rules of hot gas could not easily explain why it remained supported. In the Sun, thermal pressure from hot plasma helps resist gravity. In a white dwarf, fusion has ended, and the star is packed far beyond the density of ordinary gas. Heat alone should not be enough. The answer lies not in chemistry, not in flame, and not in any hidden furnace, but in the quantum behavior of electrons. These electrons are no longer arranged around nuclei in the calm architecture of ordinary atoms. The pressure is too great for that. Matter in a white dwarf is crushed until atomic boundaries lose much of their old meaning. Nuclei remain, surrounded by a sea of electrons that have been forced into close quarters. Electrons belong to a family of particles called fermions. They obey the Pauli exclusion principle, a rule stating that two identical fermions cannot occupy exactly the same quantum state. The wording can sound distant, but the effect is physical. When gravity tries to squeeze electrons into less and less space, the lowest available states fill. More electrons cannot simply be placed into the same condition. They must occupy higher states, carrying greater motion, and that enforced motion creates pressure. This is degeneracy pressure. It does not come from heat in the ordinary sense. A white dwarf could cool for a long time and still resist collapse because the support is written into the allowed arrangement of the electrons themselves. Gravity presses inward, but the electrons cannot all be pushed into the same quiet condition. They answer compression with a pressure born from exclusion. The word degenerate can sound like decay, but in physics, it means something more specific. The material has entered a state where density and quantum rules matter more than temperature. In an everyday gas, heating the gas increases pressure because the particles move faster. In degenerate matter, pressure can remain strong even when the material loses heat. The star is being held up by a rule deeper than warmth. There is a stillness in that idea. A white dwarf is no longer making the light that once fed its outer layers. Its great nuclear engine is gone. Yet it does not collapse immediately into a smaller and darker object. It rests on a floor made of quantum law. The floor is invisible. It has no surface, no beams, no pillars, yet it is strong enough to hold a stellar remnant against gravity for spans of time longer than the present age of the universe. The matter inside such a remnant is dense in a way that ordinary senses resist. A small amount would carry the weight of mountains in human terms. The nuclei are crowded much closer than in rock or metal, while the electrons fill the available quantum states around them. The star becomes a compact sphere of ionized matter, cooling from the outside inward, its light fading not because the support fails, but because stored heat is slowly leaving. White dwarfs are often described as dead stars, but the phrase can be misleading if it suggests emptiness. They are active in a quieter way. Their surfaces can crystallize as they cool, with ions settling into ordered structures while electrons continue to provide support. Some pull gas from a companion star and flare briefly when fresh material burns on the surface. Some belong to binary systems where gravity exchanges matter between old remnants and living stars. Even after fusion ends, a remnant can still shape its surroundings. For the path toward neutron stars, the most important lesson is the nature of the support. The sun answers gravity with heat from fusion. A white dwarf answers with electron degeneracy pressure. This is the first quantum safety net in the lives and afterlives of stars. It appears only after matter has been compressed beyond ordinary atomic structure, and it reveals that gravity is not resisted only by fire. It can also be resisted by the permitted and forbidden states of particles. The safety net has a limit. As long as the remnant is not too massive, electron degeneracy pressure can hold. Add enough mass, and the electrons must move closer to the speed of light. The rules change in detail. The pressure no longer rises fast enough to balance the added gravity. The white dwarf approaches a boundary that cannot be crossed gently. That boundary will belong to the next stage of the story, where a limit found in starlight shows that even quantum pressure has an edge. Sirius B continues its faint orbit, dim beside its brilliant companion. It is small, hot, dense, and slowly cooling. It carries the future of the sun in miniature, though the sun's own remnant will form far from any human witness. In that pale point of light, the universe has placed a quiet demonstration of compression without collapse. Matter has been pressed until atoms have lost their familiar arrangement, and still, it holds. The star remains balanced, not by burning, but by exclusion. A white dwarf can cool for ages, but it cannot accept mass without consequence. Its balance is quiet, not infinite. The same quantum rule that holds the electrons apart also carries them toward a harder condition when gravity presses too much material into too small a space. The star does not crack like stone. It does not fold like metal. It changes through the hidden arithmetic of particles until the pressure that once answered gravity begins to lose its strength. This limit entered astronomy through the work of Subramanian Chandrasekhar, a young physicist traveling by sea from India to England in the early 1930s. During that passage, while the ship moved slowly across warm water and then toward colder northern skies, Chandrasekhar thought about white dwarfs with the new tools of quantum mechanics and relativity. Electron degeneracy pressure could support a compact star, but electrons forced to move near the speed of light would not behave like slower particles. Their pressure would not rise in the same way as density increased. The safety net would tighten, then stop being enough. The result became known as the Chandrasekhar Limit. A white dwarf can remain stable only below a mass of about 1.4 times the mass of the Sunday. The exact value depends slightly on composition, but the meaning is clear. Below the limit, electron degeneracy pressure can hold the remnant up. Above it, the white dwarf has no ordinary way to remain a white dwarf. Gravity asks for more than the electrons can give. The limit is not a wall that can be seen through a telescope. It is written into the relation between mass, pressure, density, and the quantum states of electrons. Yet it appears in the sky. White dwarfs gather around possible masses below that boundary. Binary star systems sometimes push one toward it by feeding material from a companion. The more mass the remnant gains, the smaller and denser it becomes. The star is unlike familiar objects, where adding material usually makes something larger. In a white dwarf, added mass gives gravity a stronger hand, and the remnant contracts. There is a calm strangeness in that reversal. A star becomes heavier and smaller at the same time. The electrons occupy higher and higher quantum states, moving with greater energy, resisting compression as far as the rules allow. The nuclei sit in a dense sea of charge. The surface remains hot and pale. From the outside, the change may look slow. Inside, the remnant is approaching a line that no amount of cooling can soften. For a white dwarf made mostly of carbon and oxygen, crossing that line often leads not to a neutron star, but to a different end. If the remnant draws enough material from a companion, its central density and temperature may rise until carbon ignites under degenerate conditions. Because degenerate matter does not expand and cool in the usual way at first, the burning can spread violently through the star. The white dwarf can destroy itself as a type Ia supernova, releasing a bright and regular kind of explosion used by astronomers to measure cosmic distances. The remnant leaves no compact core behind. The path to neutron stars belongs to more massive stellar cores, born inside stars far heavier than the Sunday. Their lives are shorter. Their cores grow hotter. Hydrogen gives way to helium burning, then carbon, neon, oxygen, and silicon in later stages, each one taking place under stronger pressure and on shorter timescales. Near the end, the center fills with iron group nuclei. Iron is different. Fusing it does not release useful energy for the star. It takes energy instead. The core, once supported by fusion, reaches a silence in its fuel. Heat and radiation can no longer keep pace with the inward pull. Electrons are squeezed into protons. Neutrinos pour outward. The inner core contracts until nuclear density is approached, and the collapse is halted in a sudden stiffening of matter. The outer layers, still falling inward, meet the rebounding core and the flood of neutrinos. The star is torn open from within, and its outer body is cast into space. For the sleep of the universe, even this violent event can be seen in slow aftermath rather than impact. A supernova remnant expands for thousands of years, its gases thinning, cooling, and folding into the surrounding interstellar medium. Elements made in the star and in the explosion drift outward. Oxygen, silicon, calcium, iron, and heavier traces mix with older clouds. Later, some of them will become part of new stars, new planets, dust grains, oceans, and living cells. The collapse of one core becomes material for quieter beginnings elsewhere. At the center, if enough mass remains and not too much falls back, there may be a neutron star. It is the next answer matter gives to gravity after electron degeneracy fails. The electrons that once helped hold a white dwarf apart are no longer free to provide the main support. Many have been forced together with protons, making neutrons and releasing neutrinos. The star that remains is smaller than a city in width, yet holds more mass than the Sunday. The old language of atoms has almost disappeared. Chandrasekhar's limit, therefore, marks more than the boundary of white dwarfs. It marks a change in the kind of physics required to describe a dying star. Below it, electrons can hold a compact remnant in a long cooling pause. Above it, matter must either burn, collapse, or find a deeper support. The universe does not move from one state to another by preference. It follows what pressure permits, what gravity demands, and what quantum rules allow. There is a thread connecting the living sun, the white dwarf, and the neutron star before it is born. In the sun, heat from fusion answers gravity. In the white dwarf, electrons answer through exclusion. In the collapsing core of a massive star, even that answer fades, and the particles are pressed toward a denser form. Each stage is a temporary agreement. Each agreement has a boundary. The pale light of a white dwarf can therefore be read as a pause between fire and collapse. It is the cooled core of a star that found support after fusion ended. It can last for longer than galaxies keep their present shapes, fading slowly into darkness. Yet if mass is added beyond the permitted line, the quiet remnant cannot remain as it was. A threshold has been crossed. The next form must begin. Far away, in clouds left by massive stellar deaths, that next form is already present. A small object spins in the center of old debris, dense beyond ordinary comparison, held together by gravity, and held apart by rules still more severe than those inside Sirius B. The white dwarf has shown the first quantum floor. The neutron star waits below it. In the remains of a massive star, silence does not arrive all at once. Long after the central collapse, light still moves through the expanding cloud, striking knots of gas and dust that were once buried inside the star's own body. Filaments spread outward in red, blue, and pale green arcs. Some regions glow where oxygen has been heated. Others carry sulfur, silicon, and iron into the surrounding dark. The whole structure drifts, like a slow flower opening in space, though the event that made it began in a core no wider than a small planet. The Crab Nebula is one of the clearest examples of such a remnant. In the year 1054, a new light appeared in the sky bright enough to be seen during the day. At its center sits a compact object, not a white dwarf, and not a living star. It is a neutron star, the dense leftover core of a massive star that crossed beyond the support of ordinary fusion and beyond the support of electrons. Before that compact remnant forms, the center of the dying star passes through a final sequence of change. The outer layers still contain heat, motion, and shells of burning material, but the core has become dominated by iron group nuclei. Earlier fuels could release energy as they fused into heavier elements. Iron stands near the bottom of that path. Pressing iron into still heavier nuclei no longer helps the star hold itself up. The old source of outward pressure weakens, and gravity begins to draw the core inward with less resistance. At first, the collapse is a matter of density. Atoms are squeezed closer. Electrons, once spread through the material, are forced into more crowded states. The nuclei are packed nearer together, and the separations that once made matter feel spacious begin to shrink. In ordinary life, even solid metal is mostly empty space at the atomic scale. In a collapsing stellar core, that emptiness is taken away. Matter is pressed toward a condition where the old image of atoms can no longer hold. Then the electrons begin to disappear from the story in a new way. Under the pressure of collapse, many are driven into protons. Together they form neutrons, releasing neutrinos that rush outward through the falling material. This process is called electron capture, but the phrase is gentler than the change it names. The particles are being forced by gravity into a state where charge itself is reduced, where separate protons and electrons give way to a denser population of neutral particles. The neutrinos carry away energy and help the star's outer layers escape. For a brief time, The collapsing core is filled with a storm of these nearly untouchable particles. Most matter is almost transparent to them, yet in such density even neutrinos cannot pass entirely without effect. Some scatter, some deposit energy. Their presence helps turn inward collapse into outward release, though the full details remain a subject of careful modeling. At the center, the collapse stops only when matter reaches nuclear density. The core stiffens. The inner material, falling inward at great speed, can go no farther in the same way. It rebounds against the sudden resistance of nuclear matter. The outer material still falling in meets this rebounding inner region, and a shock begins its outward path. The star's envelope is thrown into space, seeded with elements made during its life and in the final explosion. Seen in later ages, the aftermath is slow and almost tender. A supernova remnant spreads into the interstellar medium. Its edges blur. Its gases mix with older clouds. Heavy elements leave the place of their making and become part of the wider galaxy. Calcium, iron, and oxygen travel outward from a place where a star could no longer support itself. The object left behind is easy to misunderstand from its name. A neutron star is not a smooth ball made only of neutrons. It begins as a remnant where neutrons dominate, but protons, electrons, nuclei, and other particles still appear in different regions. The outermost layers are shaped by radiation, magnetic fields, and remaining charged particles. The crust can contain atomic nuclei arranged in a lattice, surrounded by free electrons. Deeper down, neutrons leak out of nuclei and form a dense fluid. Lower still, the material may become stranger than any substance that can be made on Earth. The name is therefore a first approximation, not a full description. It points toward the main transformation of the collapse, the merging of electrons and protons into neutrons, but it does not capture the layering that follows. The star is more like a sequence of states arranged by pressure. Each depth asks matter a different question, and matter answers with a different form. Near the surface, it still carries traces of atomic structure. Farther in, nuclei stretch and deform. The support of this remnant comes from another quantum rule. Neutrons, like electrons, are fermions. They cannot all occupy the same quantum state. When gravity compresses them, they resist being crowded into a single condition. This neutron degeneracy pressure helps hold the star up, joined by the stiffness of nuclear forces at very short distances. It is a deeper safety net than the one inside white dwarfs, because the material has crossed beyond electron support into the domain of nuclear matter. The scale of the remnant makes the idea feel almost unreal. A mass greater than the sun may be contained within a sphere comparable to a city. Its gravity bends light. Its surface holds matter so tightly that escape would require a speed close to that of light. The star can rotate many times in a second, because the angular momentum of a much larger core has been folded into a small body. Its magnetic field may become strong enough to guide beams of radiation from the magnetic poles. If those beams sweep across Earth, instruments detect pulses. The neutron star becomes a pulsar, a clock made from a dead stellar core. The pulses can be steady enough to measure tiny changes in rotation, orbital motion, and the surrounding space. In the Crab Nebula, the central pulsar turns about 30 times each second, sending its rhythm through the remnant around it. The gas cloud glows. The small core keeps time. There is no need for the neutron star to be imagined as a final answer. It is a pause at a denser level of balance. The white dwarf showed that electrons can hold up a dead star for a very long time. The neutron star shows that, when electrons are no longer enough, matter may find another way to resist gravity. Yet this new balance is narrow. It exists between the failure of lighter remnants and the deeper pull toward black holes. It is stable only within limits that are still being measured. In the old supernova remnant, the lesson is written across two scales at once. The cloud spreads outward, thin and luminous, carrying the remains of a star into space. At the center, the neutron star remains compact, fast, and dense, holding the collapsed core in a form that ordinary matter never takes. The same event makes both the widening mist and the city-sized remnant. One part expands, one part endures. The ashes move slowly through the dark. The neutron star turns inside them, no longer burning like the star that made it, yet not empty, not simple, and not still. A neutron star is small enough for its size to be named with the language of cities. London could cover one. Tokyo could hold one inside its wider streets and harbors. A mountain road on Earth might cross from one side to the other in less than an hour. Yet within that narrow span, the star contains more mass than the Sundays. The scale bends the mind because the words remain familiar while the object does not. City, surface, crust, atmosphere, rotation. Each word arrives from the human world and then changes under the weight of the star. The surface is not a place of hills, seas, or open stone. Gravity presses downward with such severity that any raised feature is pulled almost flat. On Earth, mountains grow where crustal plates collide, where molten rock lifts, where erosion leaves hard ridges standing against wind and ice. A neutron star allows no such height. Its gravity is so strong that a mountain may rise only a fraction of a millimeter before the stress becomes too much. The star becomes one of the smoothest bodies known, not because it has no forces moving through it, but because every force is punished by weight. Smoothness does not mean softness. The crust can be rigid, locked by pressure into forms denser than any metal. A slight rise on such a surface may contain more mass than an earthly mountain range, even while it barely lifts above the surrounding crust. The word mountain survives only by comparison. It names a distortion, a tiny unevenness on a sphere where gravity has nearly erased relief. The landscape is almost level, yet it is not calm. A particle resting at that surface is held by gravity so fierce that falling becomes a different kind of motion. On Earth, a dropped stone gathers speed until air and impact end its path. Near a neutron star, the same act would become almost light-like. Matter would be dragged downward at a large fraction of the speed of light, and the impact would release energy far beyond chemical fire. The surface is therefore not merely heavy, it is a boundary where space itself seems steep. Light also feels that steepness. Photons leaving the surface must climb out of the star's gravity, losing energy as they rise. Their wavelengths stretch, their colors shift toward redder light. Some light bends around the star, so that more than one side of the surface can be visible at once to a distant observer. The neutron star does not simply sit in space, it reshapes the paths through which space is seen. The star's compactness also gives it a deep relation to time. Clocks near its surface would run more slowly than clocks far away, according to general relativity. The difference is not a matter of machinery, but of gravity's effect on the passage of time itself. A neutron star becomes a place where the rate of moments changes with height. The outer layers, the surrounding magnetosphere, and the distant galaxy do not share time in quite the same way. Then there is the spin. A massive star, before collapse, turns slowly enough for its outer layers to span enormous distances. When the core shrinks into a neutron star, that rotation is carried inward, folded into a body only a few tens of kilometers across. The result can be astonishingly fast. Some neutron stars rotate many times each second. Some millisecond pulsars spin hundreds of times each second, their surfaces moving with a speed that would tear apart ordinary matter. The star survives because its matter is not ordinary. Density, gravity, and nuclear forces bind it with a firmness no planet can approach. Still, rotation changes the shape slightly. The equator may bulge by a small amount. The crust may feel strain. If the magnetic field is not aligned with the spin axis, beams of radiation can sweep through space like a lighthouse beam passing over dark water. When the beam crosses Earth, radio telescopes receive pulses at intervals so steady that some pulsars rival atomic clocks in precision. The regularity can feel serene from far away. A pulse arrives, another follows, then another. The signal carries the rhythm of a dead star turning in darkness, its magnetic poles tracing circles through the surrounding plasma. Yet beneath that rhythm, The star is slowly losing rotational energy. It spins down over time, giving part of its motion to radiation, particles, and magnetic fields. The cosmic clock is not eternal. It is winding down with great patience. Some pulsars turn in binary systems, where a companion star feeds them gas. Material falls inward, carrying angular momentum, and the neutron star can be spun up until it becomes a millisecond pulsar. These recycled pulsars are old objects made fast again, their rotation renewed by matter taken from a neighbor. The image is quiet but strange, an ancient remnant receiving a second rhythm from another star's outer layers. The magnetic field adds another layer to the scene. During the collapse from a massive stellar core, magnetic field lines are compressed along with the matter. A field that once threaded a large star becomes concentrated into a much smaller space. For many neutron stars, the result is already far stronger than any magnetic field made on Earth. Charged particles in the surrounding region follow those lines, spiraling, radiating, and forming a magnetosphere that rotates with the star. The magnetosphere is not a hard shell. It is a moving structure of fields and particles, reaching beyond the surface into space. In some regions, electric fields pull charged particles from the crust, or accelerate pairs of electrons and positrons from empty-looking space. Radiation emerges in radio waves, X-rays, and gamma rays, depending on the star and its surroundings. The visible body is only the compact center of a wider magnetic environment. This is why a neutron star cannot be understood only as a heavy ball. It is a dense interior, a strained crust, a thin atmosphere, a curved region of spacetime, and a rotating magnetic system all at once. Its size suggests simplicity, but its behavior opens into many layers. The star is small enough to fit inside a city, yet the physics around it reaches across great distances. For the journey inward, the city-sized scale is the necessary pause. Before the crust is entered and the deeper forms of matter appear, the surface itself has to be allowed to settle into view. It is nearly smooth, fiercely heavy, slightly distorted by spin, and wrapped in fields that carry pulses across the galaxy. In that narrow sphere, gravity has taken a stellar core and pressed it until familiar size no longer means familiar matter. Even the idea of an atmosphere becomes altered here. The layer above the surface may be only centimeters thick, compressed into a film of hydrogen, helium, or heavier ions depending on the star's history. It is thin by distance and heavy by density. Radiation passes through it carrying the marks of temperature, gravity, and composition, allowing distant instruments to read the surface without touching it. The remnant turns. Its mountains barely rise. Its light climbs slowly away. Above the surface of a neutron star, the word atmosphere becomes almost too large. Around Earth, atmosphere means sky, weather, cloud, wind, and the slow blue fading of air into space. Around a neutron star, the atmosphere may be thinner than a hand is wide. It is a compressed skin of particles, held so close to the surface that height loses much of its old meaning. A few centimeters can contain a change that, on a planet, might require many kilometers. This thin layer is shaped by gravity before anything else. Hydrogen, or helium, if present, floats above heavier elements, because even in such severe conditions, lighter nuclei settle higher. Below them, heavier ions may wait in denser layers, arranged by weight and charge. The atmosphere is hot, often heated to millions of degrees, yet it is also pressed into a density that makes the word gas feel incomplete. It is not a sky in the earthly sense. It is a bright, heavy film clinging to a star that has almost no room for softness. Radiation leaves through this film, carrying marks of the surface beneath it. X-rays pass outward, altered by temperature, magnetic fields, and gravity. Some photons lose energy as they climb away. Some are bent, their paths curved by the compact mass below. To distant telescopes, the atmosphere becomes a narrow interpreter between the impossible surface and the open dark. It smooths, filters, and colors the message of the star. Just below it lies the outer crust. Here, matter begins to recover a kind of structure, though not the familiar structure of rock. Atomic nuclei remain, but the electrons are no longer bound into ordinary atoms. Gravity has pressed the material so tightly that electrons move freely through a rigid lattice of nuclei. The picture is partly like a metal, where electrons can wander, and partly unlike any metal on Earth, because the densities are far beyond terrestrial matter. The nuclei sit in ordered positions, not because the place is gentle, but because pressure has left them few other arrangements. Near the top of the crust, the nuclei may still resemble heavy atoms known from the periodic table. Iron is often imagined there, made in the earlier life or death of the star, and settled into the outer layers. Lower down, the pressure increases. Electrons are forced into nuclei more often. Protons become neutrons. The nuclei grow more neutron-rich, carrying an excess that would be unstable in ordinary laboratories, but can persist inside the star because the surroundings are so dense. Matter that would fall apart on Earth can remain held together here. The deeper descent brings the crust toward a boundary called neutron drip. The phrase sounds small, almost like moisture forming on a cold surface, yet it names a change in the identity of matter. At this depth, nuclei can no longer hold all their neutrons. Some neutrons leak out and move between the nuclei, forming a fluid that threads through the solid lattice. The crust becomes a mixture of ordered nuclei, free electrons, and a sea of unbound neutrons moving through the gaps. This is one of the first places where the neutron star begins to justify its name, not because everything has become neutron matter, but because neutrons have started to leave the confinement of nuclei. The interior is no longer only a dense arrangement of atomic pieces. It is becoming a place where parts of nuclei move independently, where the old borders between atom and surroundings become less useful. The comparison with everyday matter grows weaker with each layer. In stone, atoms hold positions in crystals or glassy forms. In metal, electrons roam, while nuclei remain in a pattern. In water, molecules turn and slide past one another. All of these familiar materials depend on atoms that still have recognizable edges, electrons that still shape chemistry, and pressures low enough for nuclei to remain small centers inside wide electronic clouds. In the neutron star crust, chemistry has mostly ended. Charge, pressure, and nuclear force have taken its place. The crust may be only about a kilometer thick, a narrow shell around a compact star. In ordinary distance, that is less than a short walk. In density, it contains layers that no mine, mountain, or laboratory chamber can approach. The upper crust is already extreme. The lower crust is more extreme still. By the time the neutron drip region is reached, the material has become a hybrid of solid and fluid, a locked lattice washed through by free neutrons. The free neutrons are expected to behave in a way that has no close household image. At sufficiently low internal temperatures, they may form a superfluid, a state in which matter flows without ordinary friction. The word low needs care in this setting, because the temperature may still be immense by human standards. Yet compared with the energy scales of dense nuclear matter, the interior can be cool enough for neutrons to pair and move collectively. A superfluid can slip through the crust's lattice with a strange independence, almost as though part of the star is able to move without dragging the rest along. This may help explain glitches in pulsars. A pulsar usually slows with great regularity as it loses rotational energy. Sometimes, however, its spin suddenly changes by a tiny amount. One possible explanation is that the superfluid inside the crust keeps its own rotation in pinned vortices while the crust slows around it. Stress builds between the two. Then, in a brief readjustment, angular momentum is transferred, and the observed pulse rhythm shifts. From far away, instruments see only a small timing change. Inside the star, different layers have quietly exchanged motion. The crust is therefore not only a shell, it is a mechanical system, a storehouse of strain, a boundary between surface radiation and deeper nuclear matter. It can crack or readjust under magnetic stress. It can hold irregularities that shape gravitational waves too faint for present instruments to detect in most cases. It can anchor magnetic fields that reach far into space. It is thin compared with the star, but not minor. There is a kind of stillness in imagining this crust. No wind moves over it as wind moves over sand. No rain touches it. No erosion softens its raised places. Yet the star is not inert. Electrons move through the lattice. Neutrons flow in hidden channels. Magnetic fields pull. Rotation slows. Heat escapes through the surface, photon by photon, while neutrinos carry energy away from deeper regions. The outer layers of the neutron star form a bridge between the known and the almost unknowable. At the top, there are particles with names that belong to ordinary physics: hydrogen, helium, iron, electrons. A little lower, the arrangements are already beyond chemistry. Lower still, neutrons begin to move outside nuclei, and the crust approaches the threshold where nuclear shapes themselves will stretch into new forms. The descent has not yet reached the core. It has only crossed the atmosphere and entered the crust. Even so, the old world of atoms has almost vanished. Matter has been pressed past air, past rock, past metal, past any state that can sit quietly on Earth. What remains is not chaos. It is order under weight, a cold architecture made from nuclei, electrons, and neutrons, held in place by gravity and by the rules that particles cannot escape. Above it, the atmosphere glows as a narrow skin. Below it, the crust waits in dense layers. Farther down, pressure will begin to bend nuclei into shapes that no ordinary matter has ever worn. Deeper in the crust, the lattice begins to lose its simple pattern. The nuclei that once sat like heavy points in a sea of electrons are squeezed closer by the growing weight above them. Free neutrons move between them. Electrons pass through the whole region with little attachment to any single nucleus. The distinction between one nuclear cluster and the next remains present, but pressure is changing the shapes that those clusters can keep. At lower density, a nucleus is close to round, because the strong nuclear force pulls its protons and neutrons inward, while electrical repulsion between protons pushes outward. The two tendencies settle into a compact shape. Inside the deep crust of a neutron star, that settlement begins to shift. The surrounding sea of neutrons presses from outside. The crowded electrons help balance charge. Gravity adds its patient demand from every direction. The nuclei are no longer isolated little islands. They are part of a thick nuclear landscape. The result, in many computer models, is nuclear pasta. The name sounds almost playful, but the material it describes belongs to one of the most severe settings in the universe. It appears where nuclei are packed so closely that they begin to merge into extended forms. Instead of separate round clusters, matter may arrange itself into rods, sheets, tubes, and bubbles. Physicists gave these shapes names borrowed from food because the real geometry is hard to picture without something familiar to hold it. Gnocchi, spaghetti, lasagna, strange names for a star's buried crust. The first of these forms may resemble small, rounded clusters, dense droplets of nuclear matter surrounded by electrons and free neutrons. With increasing depth, pressure pushes the clusters into longer shapes. Rods appear, stretching through the material like dark threads in a solid sea. Deeper still, the rods may flatten into broad sheets, stacked through the crust in layers. At still greater pressure, the pattern can invert, with voids or tubes running through denser matter. The sequence is not a recipe, and the star is not making food. It is finding shapes that reduce energy under conditions no laboratory can hold for long. There is no hand sculpting these layers, no slow geological erosion, no cooling lava, no mineral water depositing crystals in a cave. Nuclear pasta forms from the competition between nuclear attraction and electrical repulsion, between the desire of nuclear matter to gather and the refusal of protons to sit too close without cost. The shapes arise because matter seeks the lowest available energy. Under the immense pressure of the crust, that lowest energy may not be a sphere. It may be a strand. It may be a sheet. The scale is small in distance and immense in consequence. A pasta layer may be only a thin part of the crust, perhaps a few hundred meters or less, depending on the star and the chosen equation of state. Yet its density is so high that a modest volume would hold mass beyond earthly comparison. The shapes themselves are nuclear in size, far below direct sight, but together they may influence the entire star. A hidden layer, too deep for any telescope to image, can affect how the surface cools, how the crust breaks, and how the star spins down through time. Calculations suggest that nuclear pasta may be among the strongest materials in the known universe. The estimate comes not from a sample, but from simulations of dense matter under strain. In those models, the tangled rods and sheets resist breaking with enormous strength, far beyond steel or diamond. The reason is not that the material is hard in the familiar sense. It is made from nuclear forces acting across shapes, packed almost to the limit allowed before the deeper interior begins. To bend or break, it means disturbing matter, held together at a level far below chemistry. This strength may matter during starquakes. A neutron star crust is thin, but it bears stresses from rotation, cooling, and magnetic fields. If nuclear pasta lies near the base of that crust, it may act as a heavy, elastic layer, storing strain and releasing it in sudden readjustments. The motion would not resemble an earthquake on a rocky planet. There are no tectonic plates sliding through mantle. There is only dense nuclear material shifting under gravity, magnetic tension, and the slow change of a star losing heat and spin. The same layer may also influence gravitational waves. A perfectly smooth spinning sphere would not send out a steady gravitational wave. It would rotate without changing its mass pattern in a way that could ripple space-time. But if a neutron star has a slight asymmetry, even a tiny mountain or internal unevenness, its spin may create a faint signal. Nuclear pasta, if strong enough, could help the crust support those small distortions. The signals would be weak, and most remain beyond present detection. But the possibility turns a hidden nuclear layer into part of a much larger astronomical search. The pasta may also slow the escape of heat. Electrons moving through the crust can scatter from the irregular shapes, and heat may travel differently through rods than through sheets. A neutron star cooling in space, therefore, carries information about buried geometry. The surface temperature is not simply a surface fact. It is linked to the conductivity of deeper layers, to superfluid neutrons, to neutrino emission, and to the way nuclear matter arranges itself near the crust's base. A distant X-ray glow becomes a clue to shapes smaller than atoms. This is one of the quiet wonders of neutron stars. They turn almost invisible details into astronomical behavior. The rounding of a nuclear cluster, the flattening of a sheet, the frictionless motion of neutrons, the scattering of electrons through dense matter. All of it may leave traces in pulse timing, cooling curves, bursts, or waves too faint to hear yet. The star is small, but it magnifies the rules of matter until they shape objects across kilometers. The deeper crust is therefore not a simple passageway on the route to the core. It is a region with its own hidden structure, its own slow mechanics, and its own part in the life of the remnant. Above it, the outer crust still remembers nuclei as separate things. Below it, the core will become more uniform, more fluid, and perhaps more difficult to describe. Between them, nuclear pasta forms a borderland, neither ordinary solid nor smooth nuclear sea. In that borderland, matter wears shapes that no eye can see. It gathers into rods and sheets under a darkness too dense for light to cross freely. It holds stress. It carries heat. It may help a dead star keep its rhythm, or change that rhythm by a fraction so small that only long watching can reveal it. The crust grows deeper. The shapes flatten. The old roundness of nuclei gives way to gravity's patient geometry. On the outside of the International Space Station, the universe is both empty and crowded. Earth fills half the view with blue ocean, white cloud, and thin bands of atmosphere, while the black above it holds stars without twinkle. Instruments fastened to the station's frame face that blackness hour after hour, gathering kinds of light that human eyes were never made to see. Among them is a compact X-ray telescope built for one of the densest kinds of object in nature, Its name is NICER, the Neutron Star Interior Composition Explorer. The instrument does not descend into a neutron star, and it cannot touch the surface of one. It waits in orbit above Earth and reads X-rays from faraway pulsars, especially the heat and radiation that leave small bright regions on their rotating surfaces. Those bright regions pass in and out of view as the star spins. Each passing changes the arriving X-ray light by a small amount. Hidden in those changes are clues to mass, radius, gravity, and the way space-time bends close to the star. The task is delicate because a neutron star is not seen as a resolved disk. Even the nearest ones are too small and too far away. Their surfaces cannot be photographed in the ordinary sense. NICER measures patterns instead. It counts X-ray photons. It records their energies and arrival times. It watches how pulses rise, fall, stretch, and soften as hotspots rotate across the visible side of a star. The shape of the pulse is affected by the star's gravity, because gravity bends light around the compact surface. More of the star can be seen than would be possible around a less dense object. A larger star bends light less strongly than a smaller star with the same mass. A more compact star pulls the light into paths that reveal extra surface and smear the pulse in a different way. From this slow reading of brightness and timing, astronomers can estimate the radius of a neutron star, whose body remains far beyond direct sight. The method is not simple. It depends on models of hotspots, atmosphere, rotation, and general relativity, yet it gives one of the few ways to approach the hidden equation of state. The equation of state is the quiet problem underneath the whole instrument. It asks how dense nuclear matter responds to pressure. A soft equation of state allows matter to be squeezed more easily, making a massive neutron star smaller. A stiff equation of state resists compression more strongly, leaving a larger radius even when mass is high. The difference may be only a few kilometers, but in a neutron star, that difference reaches all the way into the core. A small change in measured size can rule out whole families of possible interiors. One of NICER's most important targets is the pulsar catalogued as PSR J0740 plus 6620. It is a heavy neutron star with a mass a little above twice the mass of the Sunday. That alone makes it valuable. A star so heavy presses its core into one of the most demanding natural tests of dense matter. If the interior were too soft, gravity would compress it too far, or the star might not remain stable at all. The existence of such an object already removes some possibilities. Before careful measurements, many models suggested that the heaviest neutron stars should be among the smallest. More mass means stronger gravity. Stronger gravity should squeeze the material inward. The thought is natural, and for many kinds of matter it would be enough. Yet NICER's observations of PSR J0740 plus 6620 indicated that it is not as small as many softer models expected. Its radius appears broadly similar to that of less massive neutron stars measured by the same mission. The heavy star did not shrink in the simple way. The result does not mean that the answer is known. It narrows the path. It suggests that, at least over some range of density, the matter inside neutron stars may resist compression more strongly than some theories allowed. The core may be stiffened by nuclear interactions, by the behavior of neutrons and protons at close range, or by more unusual ingredients that do not soften the star as much as older pictures predicted. Every possibility must still pass through the same narrow gate of mass and radius. NICER's work also shows why neutron stars cannot be understood only through one object. Another pulsar, lighter and spinning quickly, gives a different measurement. Gravitational waves from merging neutron stars add another constraint. Cooling stars add another. Each observation is partial, shaped by its own uncertainties, but together they form a tightening net around the equation of state. Some models remain possible, others fall away quietly, not from a single dramatic proof, but from the patient accumulation of incompatible details. The instrument itself has had its own fragile story. In 2023, Damage to thin thermal shields allowed unwanted sunlight to leak into the detector. The effect made some observations harder, especially when the station moved through bright orbital conditions. Later, astronauts repaired the shielding in orbit, working outside the station where tools, gloved hands, and small parts had to be managed against the curve of Earth. The repair did not change the nature of neutron stars, but it allowed the telescope to keep listening to them. There is a soft contrast in that scene. A human-made instrument, small enough to fit on a space station, circles Earth every day and gathers X-rays from stellar remnants that are heavier than the Sun and no wider than a city. The telescope is delicate. The objects are dense beyond ordinary thought. Between them lies a long thread of timing, counting, modeling, and inference. No sample travels from the pulsar to the detector. Only light arrives, bent by gravity, filtered by atmosphere, and marked by the spin of the star. For PSR J0, 740 plus 6620, the light says that the star remains large enough to trouble simple expectations. Its core may not be the easily compressed sea once imagined. The pressure at depth may rise more firmly. The star may be carrying a hidden resistance, a dense answer to gravity written in nuclear matter. If particles in the core change form, they must do so without making the star too soft to survive its own mass. This is the reason such measurements matter, though the script of the star remains hard to read. The radius of a neutron star is not merely a number. It is a shadow cast by the interior. It carries information about neutrons, pairing, protons, mixing, possible exotic particles, and the force between pieces of matter pressed nearly as close as nature allows outside a black hole. A few kilometers become a map of physics that cannot be reproduced on Earth. NICER keeps watching as the station moves through sunlight and darkness. Pulses arrive from compact stars scattered through the galaxy. Some are steady. Some carry changes in heat or timing. Each one adds a small mark to the larger picture. Beneath the X-ray curves, beneath the careful models, a simple image remains. A heavy neutron star that should have been smaller, still holding its size against gravity. The surface turns. The hotspots pass into view and away again. Far inside, the core keeps its secret a little longer. Below the crust, the neutron star enters a deeper and less certain country. The nuclear pasta fades into a more uniform fluid. Though uniform does not mean simple, neutrons dominate the pressure and mass, but they are not alone. A smaller number of protons remains mixed through the interior, along with electrons and perhaps muons, heavier cousins of the electron that appear when density raises the energy of the particle C. The core is not a chamber with walls. It is a change in conditions, a region where the spacing between particles has become so small that the boundaries of nuclei no longer matter. In this inner ocean, neutrons may form a superfluid. Protons may form a superconducting component, carrying electric current without ordinary resistance. The language is borrowed from laboratories, where superfluid helium can climb surfaces and superconductors can guide magnetic fields in strange ways, but the neutron star version exists under pressure far beyond those experiments. Inside the star, paired particles move collectively through matter that is already close to nuclear density. Motion becomes less like grains sliding past grains and more like a single hidden order running through the depth. The core matters because it decides the star's answer to gravity. If pressure rises strongly as density increases, the star remains larger and more difficult to compress. If pressure rises more weakly, the interior is softer, and gravity can draw the surface inward. This relation is the equation of state, and it is still an open problem in astrophysics. The difficulty is not only that the core cannot be reached, it is that the same mass and radius can sometimes be produced by different internal recipes, leaving only faint traces in light, timing, waves, and cooling. For many years, one natural expectation was that deeper pressure would break neutrons and protons into their smaller pieces. A proton is made of quarks. A neutron is also made of quarks. In ordinary nuclear matter, those quarks are confined inside the particles, bound so tightly that they do not roam freely as separate things. Near the center of a heavy neutron star, where density climbs beyond the density inside atomic nuclei, the old particles may begin to lose their separate identities. The core may pass into quark matter, a dense fluid where quarks are no longer locked inside individual neutrons and protons. The image is not one of tiny beads cracking open like shells. Quantum fields do not behave with such clean edges. It is better to picture a crowd so compressed that individual rooms no longer define the movement of the people inside them. The distinctions that once mattered become blurred by density. Quarks that were once associated with separate particles may instead belong to a wider state of matter. The change, if it occurs, would be a phase transition, a crossing from one arrangement to another inside the same compact star. Yet this possible crossing brings a difficulty. New forms of matter do not automatically make a neutron star stronger against gravity. In many models, quark matter softens the equation of state. Energy is spent changing the internal structure of the particles, and the resulting pressure may not rise quickly enough with density. A softer core would allow the star to become smaller. For very massive neutron stars, especially those above twice the mass of the Sun, too much softness becomes dangerous. The object would struggle to remain a neutron star at all. This is one of the quiet reversals in the subject. Stranger matter is not always a stronger safety net. The deeper ingredient may make the star less able to hold itself up. A core filled too easily with deconfined quarks could conflict with the existence of heavy neutron stars whose measured sizes suggest a stiff interior. The possible quark core must therefore be subtle. It may appear only at very high density. It may be mixed with ordinary nuclear matter. It may change the star, without weakening it beyond survival. Hyperons bring a related problem. These particles resemble protons and neutrons in belonging to the baryon family, but they contain strange quarks. On Earth, hyperons are short-lived, appearing in high-energy experiments or cosmic ray interactions before decaying. Inside a neutron star core, the surrounding pressure may make some of them stable enough to persist. Their appearance would give the dense matter new ways to arrange energy. Particles that were absent at lower density could begin to share the burden of the core. At first, that seems helpful. More particle types might sound like more support. The opposite often happens. When hyperons appear, the material can place energy into new particle states rather than forcing existing neutrons into higher pressure. The equation of state can soften. The core becomes more compressible, and the maximum possible mass of the neutron star may fall. This tension is known as the hyperon puzzle. The particles are physically plausible, yet their presence can make it harder to explain the heaviest neutron stars already observed. The puzzle does not require a single answer. Some models give hyperons extra repulsive interactions at high density, stiffening the matter again. Some delay their appearance until densities reached only in the deepest cores. Some allow a transition to quark matter that becomes stiff after the crossing. Each path is a different attempt to let the star contain strange ingredients without collapsing too soon. The sky keeps removing the easier answers. Heavy pulsars, radius measurements, cooling curves, and merger waves all press the theories into narrower shapes. There may also be matter inside the core that carries no light at all. Dark matter, if it interacts weakly with ordinary particles, could gather inside massive stars before they die and remain trapped after collapse. A small, dark component in a neutron star might alter the mass-radius relation, either softening or stiffening the effective response depending on the kind of dark matter assumed. This idea remains tentative, but it shows how neutron stars reach beyond nuclear physics into the wider unknown matter of the universe. The core is therefore not a single hidden object waiting to be named. It is a set of possibilities arranged by density, pressure, particle identity, and the limits of present observation. Ordinary nuclear matter may persist farther inward than expected. Hyperons may appear and be restrained by repulsive forces. Quarks may become partly free without making the star too soft. Dark matter may add a faint invisible contribution. None of these options can be accepted because it sounds strange. and none can be dismissed only because it is difficult to picture. At the center of the neutron star, the old world has almost no remaining shape. There are no atoms, no chemistry, no minerals, no plasma in the solar sense. There is dense quantum matter answering gravity in the only ways allowed to it. The core does not shine outward with a visible surface. It speaks through the size of the star, through the rhythm of pulses, through the way heat escapes, and through the waves released when two such remnants meet. The descent pauses there, not because the mystery ends, but because the material has entered a region where images must grow quieter. Matter is still present. Pressure is still rising. Gravity is still asking for collapse. Somewhere inside, the star finds enough resistance to remain itself, a dark, compact body held between the known particles of the laboratory and the unknown behavior of nature at its densest edge. Some neutron stars carry magnetic fields so strong that the field becomes part of the star's structure, not only a surrounding feature. These objects are called magnetars. They are still neutron stars, still compact remnants of massive stellar cores, still held up by dense matter resisting gravity. Yet their magnetic fields rise far beyond those of ordinary pulsars, reaching strengths that change the behavior of the crust, the atmosphere, and the space around them. A magnetic field is often imagined as something light and invisible, lines drawn around a bar magnet in schoolroom diagrams, iron filings curving into neat arcs. Around a magnetar, that simple image fails. The field stores enormous energy. It twists through the crust and reaches outward into the magnetosphere, pulling charged particles into motion and shaping the escape of radiation. The star is small, but the magnetic structure around it can reach far beyond the surface, a dark architecture made of force rather than matter. The origin of such fields is still studied. A newborn neutron star may inherit and amplify the magnetic field of its parent star during collapse. As the stellar core shrinks from a great radius into a sphere only a few tens of kilometers across, magnetic flux is compressed. A field that was once spread through a large volume becomes concentrated into a tiny one. Rapid rotation in the first moments after birth may also help strengthen the field through dynamo action, with turbulent motion inside the young remnant winding and feeding magnetic energy before the star settles into its longer life. In a magnetar, the magnetic field does not sit quietly above the crust. It threads the star and strains it. The crust is dense and rigid, but not free from stress. Magnetic forces can pull against it from within and above, slowly changing the balance of the surface layers. The crust resists for a time. It holds the deformation, much as cold ice can hold pressure before it shifts. Then, a small readjustment may occur. The surface moves. The magnetic field reorders. Energy leaves in X-rays and gamma rays. These events are sometimes called starquakes. The word borrows from Earth, but the comparison is limited. An earthquake comes from rocky plates, faults, friction, and the slow motion of a planet's interior. A starquake in a magnetar belongs to nuclear crust, magnetic tension, and gravity so strong that the surface can hardly rise. The motion may be small in distance, but the stored energy can be immense. A slight change in a crust only a little out of shape can light the surrounding space. The emission does not always arrive as a single great flash. Magnetars can produce repeated bursts, irregular pulses, and long changes in brightness. Their X-ray output may fade slowly after an active episode, as heat moves through the crust and the magnetosphere relaxes. The star seems to remember the disturbance. Radiation decreases over months or years, carrying the thermal echo of strain released below the surface. In this way, a magnetar is not merely seen at the moment of activity. It can be watched as it settles. The crust has a special role in that settling. Heat deposited below the surface must travel outward through layers of dense matter, electrons, nuclei, free neutrons, and perhaps nuclear pasta near the base. The way the heat spreads depends on conductivity, magnetic geometry, and the state of the matter itself. A hotter region may rotate into view and then away, producing changes in the X-ray pulse shape. Distant instruments read these changes as softened light and shifting timing, but inside the star, they trace the path of heat through a shell no ordinary material can resemble. The magnetosphere also changes. Around an ordinary pulsar, magnetic fields guide beams of radiation from the poles. Around a magnetar, the external field can become twisted. Charged particles flow along those twisted lines, scattering radiation from the surface and altering the spectrum that reaches telescopes. A pulse from a magnetar is therefore not only a surface signal, it is surface light processed through a charged magnetic environment, a message shaped twice before it crosses interstellar space. Some magnetars rotate slowly compared with millisecond pulsars. Many turn once every few seconds, not hundreds of times each second. Their power is not mainly drawn from rapid spin, it comes from magnetic energy. This separates them from ordinary rotation-powered pulsars, whose radiation is fed by the gradual slowing of the star's rotation. In a magnetar, the field itself is the reservoir. The star shines and bursts because its magnetism is decaying, rearranging, and releasing stored stress. That decay also gives magnetars a kind of lifetime. Their strongest activity may last only a small part of the neutron star's existence. As the field weakens over thousands of years, the bursts may become less common, the persistent X-ray glow may fade, and the object may begin to resemble quieter neutron stars. The boundary between magnetars and other pulsars is not perfectly sharp. Some ordinary-looking pulsars show magnetar-like activity. Some magnetars become quiet enough to hide among less active remnants. Nature does not always keep categories clean. The connection reaches into fast radio bursts as well. Some short radio flashes from deep space may come from magnetars, especially young and strongly magnetized ones. In the Milky Way, a magnetar produced a powerful radio burst in 2020, linking at least some of these mysterious signals to neutron stars with extreme fields. The event did not solve every fast radio burst, because the universe rarely offers only one path for a phenomenon. It did show that a magnetar can send a brief radio pulse across vast distances, sharp enough to be noticed after traveling through the galaxy. Even so, the sleep of the star remains slow beneath the bursts. A magnetar is not active every moment. For long periods, it turns in darkness, its crust carrying old stresses, its field lines extending into the surrounding space, its heat leaking outward through dense layers. The sudden flashes are only visible signs of longer internal changes. Behind them is a remnant cooling, spinning down, and allowing its magnetic field to unwind through time. In the larger story of dense matter, magnetars reveal that pressure is not the only force shaping a neutron star. Gravity sets the scale. Degeneracy and nuclear forces help support the interior. Rotation gives rhythm. Magnetic fields add tension, heat, and sudden rearrangement. The star is a meeting place of all these influences, each one strong enough to leave a mark on the others. A magnetar, therefore, turns the crust into more than a boundary. It becomes a strained surface where the hidden interior and the outer magnetosphere speak to each other. A shift below can brighten space above. A twist in the magnetic field can warm the surface. A faint change in pulse shape can tell of geometry that no image can show directly. Far from any planetary sky, the magnetar continues its slow work. The field pulls, the crust holds, heat moves outward in narrow paths. Then, after a long quiet interval, a small part of the star adjusts, and a wave of high-energy light leaves the surface, crossing the dark as a brief sign of pressure, magnetism, and matter under strain. When two neutron stars draw close to one another, the motion begins long before the final meeting. For millions of years, or sometimes for far longer, they orbit a shared center of mass in the dark. Each star is compact, heavy, and small, carrying the remnant core of a massive stellar death. Around them, space is almost empty. Between them, gravity is always working. taking a little energy from the orbit and sending it outward as ripples in space-time. Those ripples are gravitational waves. They are not waves moving through air or water. They are changes in the shape of space-time itself, stretching and squeezing distances by amounts far too small for ordinary senses. A pair of neutron stars loses orbital energy through these waves, and as energy leaves, the stars fall closer together. The orbit tightens, the rhythm quickens, the waves rise in frequency, like a faint chirp climbing toward its last note. For most of the long spiral, nothing in the surrounding sky may appear changed. The stars are too small to see directly. Their surfaces are hidden by distance, yet their gravity is already writing a signal across the universe. Each orbit sends another ripple outward. The pattern carries information about the masses of the stars, their separation, and, near the end, the way their dense interiors resist being stretched by one another's tides. Even before they touch, the stars are testing the equation of state. A softer neutron star, more easily deformed, answers tidal pull differently from a stiffer one. During the last moments of approach, each star raises a tiny tidal bulge on the other, not like ocean tides on Earth, but as a distortion of dense matter and space-time. That distortion changes the gravitational wave signal. The effect is faint, but it matters. In the waveform, astronomers can search for signs of how strongly the stars yielded before merging. The secret of the interior becomes part of the shape of a passing wave. In 2017, such a signal reached Earth from the galaxy NGC 4993. The event became known as GW 170817. Two neutron stars had spiraled together and merged about 140 million light-years away. The gravitational waves arrived first, recorded by detectors built to measure changes smaller than the width of a proton across long arms of laser light. Less than 2 seconds later, a short gamma-ray burst came from the same region of sky. That close timing mattered. It showed that gravitational waves and light had crossed the same vast distance at nearly the same speed. It also joined two kinds of astronomy that had often worked apart. One signal was a ripple in space-time. The other was electromagnetic radiation, first in gamma rays and then across X-rays, ultraviolet light, visible light, infrared, and radio. The same event spoke in more than one language. This is multi-messenger astronomy. The phrase can sound technical, but the image is simple. A distant collision sends several kinds of news at once. Gravitational waves carry the motion of the masses. Light carries the heat, debris, and radioactive glow. Neutrinos may also carry messages in other events. No single messenger gives the whole scene. Together, they allow the hidden process to be reconstructed with less guesswork and more care. After GW 170817, telescopes across Earth and in space turned toward NGC 4993. They found a fading point of light, a kilonova, made by material thrown out during and after the merger. The glow changed color as days passed. At first it was hotter and bluer. Later it reddened, cooled, and faded into infrared light. Inside that changing glow, heavy atomic nuclei were being made and decaying, releasing energy as the debris expanded into space. The making of heavy elements is one of the gentler consequences of a violent meeting. Neutron-rich matter, flung from the merger, becomes a place where atomic nuclei can capture neutrons very quickly. This rapid process builds elements heavier than iron. Gold, platinum, and other heavy nuclei may form in such events before dispersing through interstellar space. Long after the light fades, some of that material may become part of dust, planets, oceans, or the small bright ring on a human hand. A collision between dead stars can leave traces in quiet rooms. The merger also tests the maximum mass of neutron stars. When two remnants combine, the result depends on total mass, rotation, temperature, and the equation of state. For a brief time, the merged object may be a hypermassive neutron star, supported by rapid rotation and intense heat. It may wobble, shed matter, and radiate before collapsing. Or If the mass is too high and support fails quickly, a black hole may form soon after the stars meet. The boundary is still being narrowed. In GW 170817, the observations suggest that the merged object did not remain as an ordinary stable neutron star for long. The total mass was too high for a quiet, lasting remnant under most equations of state. Some short-lived intermediate state may have existed, hot and rotating, before collapse. The absence or presence of signals from such brief remnants helps astronomers test how much mass-dense matter can support. Even what is not seen can carry meaning. Around the newborn central object, an accretion disk of torn material may form. Some matter falls inward. Some is blown away in winds. Some escapes in narrow jets or wider outflows, carrying energy into the surrounding dark. The gamma-ray burst likely came from a fast jet connected to the merger, though the exact geometry required careful interpretation because Earth did not look straight down the jet's center. The event was not a simple firework. It was a layered outflow, changing with angle, time, speed, and composition. For sleep narration, the most lasting image is not the impact itself, but the fading afterglow. A small point in an old galaxy brightens and then slowly dims. Beneath that fading light, dense matter has crossed another threshold. Two separate neutron stars have become one short-lived remnant, or a black hole, or both in sequence. Gravitational waves have moved on, widening through the universe. Heavy elements drift outward, no longer bound to the place of their making. The evidence is delicate, but it is not distant in meaning. It turns one brief meeting in another galaxy into a measure of pressure, density, gravity, and the hidden stiffness of matter. The stars that met are gone as separate bodies. Their signal remains in detectors, in models, in spectra, and in the quiet understanding that matter under pressure can reveal itself even at impossible distance. A ripple reaches Earth. A point of light fades. Somewhere between them, the interior of a neutron star has left its trace. Some neutron stars grow quiet enough that their strongest message is heat, leaving slowly. They no longer shine with the fresh violence of a supernova remnant. Their magnetic fields may be less restless than a magnetar's. Their pulses may be faint or absent, yet the surface still carries a temperature, and that temperature is not only a surface fact. It is the last visible trace of processes buried deep inside the star. A newborn neutron star is hot beyond ordinary comparison. The collapse that made it leaves dense matter filled with thermal energy, and for a short time the remnant glows strongly in X-rays. But the heat cannot stay. The star cools by sending photons from its surface and by releasing neutrinos from its interior. Photons leave from the outer layers, carrying energy into space as radiation. Neutrinos escape from deeper regions, often far more efficiently, because they interact so weakly with matter that they can slip out from places light cannot cross. The balance between these cooling paths depends on the interior. If the core allows certain neutrino processes to happen quickly, the star can lose heat much faster. If those processes are blocked by composition, superfluid pairing, or the absence of particular particles, the cooling is slower. A cooling curve, drawn from surface temperature and estimated age, becomes a quiet graph of hidden matter. The star's fading warmth carries information about particles that no telescope can see directly. This makes old neutron stars valuable in a different way, from heavy pulsars or merging binaries. A massive pulsar tests how much pressure dense matter can provide against gravity. A merger tests how easily the star deforms and how much mass survives before collapse. A cooling neutron star tests the channels through which energy leaves the core. 3 paths, 1 hidden interior. Recent observations have sharpened that cooling test. A small group of neutron stars has been found colder than expected for their estimated ages, by factors large enough to remove many possible models of dense matter. Their surfaces appear to have lost heat too efficiently for ordinary slow cooling alone. The result points toward faster neutrino emission in the interior, or to a combination of composition and pairing that opens a hidden drain for energy. The stars are not strange because they flare. They are strange because they are too cold. There is something especially fitting about this clue. The deepest matter in the star does not reveal itself by brightness, but by absence of warmth. A surface dimmer than expected becomes a message from the core. The light that is missing narrows the forms that matter can take. Models that once seemed possible no longer cool the star in the right way. Others remain, waiting for better measurements, more ages, more temperatures, and more careful comparisons. Cooling is shaped by superfluidity as well. When neutrons pair in the core or crust, and protons enter superconducting states, the heat capacity of the matter changes. Some neutrino processes are suppressed. Others can appear when pairs form and break. The star becomes thermally layered, not only by density, but by the collective behavior of particles. A transition that occurs far below the surface can alter the pace at which the whole remnant fades. The crust also plays its part. Heat made or stored below the surface must travel through dense layers before it can leave as photons. In some neutron stars that accrete matter from companions, outbursts heat the crust, and later observations watch that crust cool back toward the core's temperature. The decline is gradual. It allows astronomers to estimate thermal conductivity, impurity content, and the way heat moves through matter beyond ordinary solids. A cooling crust becomes a thermometer inserted into a star that cannot be touched. All these clues press on the same unresolved boundary. A neutron star can remain a neutron star only below a maximum mass. That boundary is often called the Tolman-Oppenheimer-Volkoff limit, though its exact value depends on the equation of state. If dense matter is stiff, the limit is higher. If it is soft, the limit is lower. Rotation can help support extra mass for a time, and heat can help briefly after a merger, but neither support lasts forever. The star must eventually settle into what its cold, dense matter can hold. Near that boundary, the possibilities narrow. A stable neutron star remains, compact and cooling. A temporary remnant may persist if rapid rotation spreads the burden. A more massive object may cross into collapse, forming a black hole. Between these outcomes, there may be intermediate states, quark matter, hybrid cores, or other dense arrangements that alter the path without removing the final question of support. The line is not drawn by a single number alone. It is drawn by mass, spin, temperature, composition, and the pressure of matter at densities higher than atomic nuclei. Black holes mark the point where no known internal pressure can hold a star open. For a distant observer, the collapse leaves an event horizon, a boundary beyond which light no longer returns. The details inside that boundary belong to a region where present theories do not yet fit together with ease. General relativity describes gravity with great accuracy outside the horizon. Quantum mechanics describes matter and particles with equal strength elsewhere. In the deepest collapse, both are needed, and their disagreement becomes unavoidable. Neutron stars stand just before that final darkness. They are compact enough to test gravity, dense enough to test nuclear matter, and visible enough to offer signals. Their light can be measured, their pulses can be timed, their mergers can be heard in gravitational waves, their cooling can be tracked across years. They are not hidden behind horizons, and so they remain available to patient observation. The oldest among them may eventually grow very cold. Their surface photons weaken, their spin slows, their magnetic fields decay or settle. Some may become difficult to find at all. Small, dark remnants, moving through the galaxy with little radiation left to announce them. Yet even as they fade, the physics they contain does not become less exact. The dense core remains a record of the rules that allowed matter to stop short of collapse. In that fading, the journey finds its softest ending. The path began with sunlight, with plasma and fusion holding a living star in balance. It passed through white dwarfs, where electrons resisted compression, and through neutron stars, where nuclear matter answered gravity more severely. It moved across crust, pasta, core, magnetar, merger, and cooling surface. Each stage showed matter, searching for another form of support. A cold neutron star is not empty. It is an agreement still being kept in darkness. Gravity presses inward. Quantum rules and nuclear forces answer from within. Heat leaves slowly, carrying the last accessible signs of the deep interior. Somewhere below the surface, in matter beyond chemistry, the star remains balanced near the edge of what a star can be. The X-rays fade, the pulses lengthen, the remnant cools, and the universe keeps its quiet watch. Long after the first light of a star has faded, the matter it shaped continues in quieter forms. Some of it drifts outward as gas and dust, joining the wide clouds between stars. Some remains locked in small, compact remnants, white dwarfs cooling like hidden embers, neutron stars turning slowly in the dark. The universe does not erase these endings. It folds them into its larger motion, layer by layer, until collapse, pressure, heat, and time all become part of the same long stillness. A neutron star resting far from any bright nebula may no longer draw attention from the sky around it. Its surface cools, its magnetic field weakens. Its pulses, if they remain, arrive with a rhythm almost too patient to notice. Inside, matter still holds its dense agreement. Gravity presses inward, and the particles answer, not with flame, not with chemistry, but with the quiet resistance of quantum rules and nuclear force. The star is small. The silence around it is wide. Elsewhere, sunlight still falls on planets. Oceans move beneath moons. Dust crosses empty space and settles into new beginnings. The atoms made in older stars travel on, joining stones, clouds, metal, water, and living forms that will never feel the pressure of a neutron star core, yet still belong to the same physics. The distant remnant and the warm world are not separate stories. They are different layers of one universe. Now the image can become simple again. A dark sky, a cold star, a faint pulse crossing a field of night. No hurry remains in it. Only the slow release of heat, the soft passing of time, and matter resting as close as it can to the edge of collapse without falling through.